Buddy, today we're gonna do problem. Let's get me in this screen fully. Yeah, so today we're gonna do problem 2054, two best non-overlapping events. Now this problem is stated as a medium, but I would argue that this is a hard. Um, this is a very difficult problem. I had a lot of trouble. Full disclosure, right? I've already solved this, and this wasn't a medium to me. This was a hard. But I've had a I've beaten that dead horse in terms of describing how terrible I think the classification system is. That there's just easy, medium, and hards, right? I mean, many of you probably have experienced this where a medium is more difficult than a hard, and a hard is easier than a medium. Even some easies are hards. You know, it's not really a fair classification system, but whatever. So it's a hard problem, so let's just go ahead and get right into it. So you're given a zero index 2D integer array of events where events I equals start time, end time, and value I. So basically there's an event, it starts at a certain time, it ends at a certain time, right? And then there's some sort of award you get, which is value associated with attending that event. The ith event starts at start time and ends at end time. Okay, if you attend this event, you receive a value of value I. You can choose at most two non-overlapping events to attend such that the sum of their values is maximized, right? So it's like a scheduling problem, right? You could look at, maybe you have two people that want you to tutor them in software engineering, right? And they have different time slots that they want, and you can only choose a maximum of two people, right? Two people that you're willing to help, and the maximum award you can get, right, by helping them. So now I'm starting to think about a different solution that I didn't use to solve this, but whatever. Because I think there might be a greedy solution. I don't know though. Return this maximum sum. Okay. Note that the start time and end time is inclusive. That is, you cannot attend the two events where one of them starts and the other ends at the same time. More specifically, if you attend an event with end time t, the next event must start at or after t plus 1. Okay, so like I can't, like if this thing, it goes through 3, right? So this event starts at time 1 and it ends at 3, but it goes through 3, right? So if an event started if the next event started at 3, there would be a collision. All right, so for this example, the output's 4, right? Because you would go to event 0, collect 2 points, and then go to event 1 and collect 2 points. For this example, you could do event 0, collect 2 points, but then you wouldn't be able to get this 5, and then you could also do this and collect 2 points, so you get 4 in total, but that's less than 5. So you can choose at most 2 events, but I guess you can also just choose 1. Right. Here, what's the situation? Take 3 and 5, that gives you 8, right? So these are at the same time, but it's better to take 3 and 5 versus 1 and 5. And yeah. Okay. Oh my gosh. So the easiest solution here, right? It says n squared would be to just look at each pair of events, right? So n choose 2, n squared. So look at each event and then compare it to all the other events, and then just filter out the ones that collide, right? That their times, they share a time. If they don't share a time, then just find the sum of those two events and do that for each event. So that's n squared time. And that's probably the most intuitive approach, right? Like, look at this event, then look at each other event and compare it to this event. If they collide, you can't consider it. If they don't collide, then you can consider it as a max, and then take the max of each pair of events. Okay, but that isn't the approach that is quicker. So there's an n log n approach, and the idea is basically, imagine you had these events, right? A, Z, X, and Y. Now I'm giving them random names, right? So you have an event A, an event Z, an event X, and an event Y. Okay. Now I wrote them in order, right? Because I had to write them in some order. But we don't really know. Let's say we don't know, like, we haven't. I'm not making any claim about which event comes first, which event ends first, right? It could be that X is first and ends first, right? There could be all sorts of orders to these events. I'm just saying that each of these letters represent an event, right? An event has a start time, an end time, and an award, a value associated with it, right? Well, what can we say about choosing any two event? Well, if we choose any two event, well, we first have to choose one event, and then the n squared idea was you choose an event, and then you compare it to each other event and see if it works. Then you look at this event and compare it to each other event and see if it works. So that's n squared time, right? So maybe what could be helpful here is if I say I look at each event for each event. So this is the n squared solution. Event B not equal A. Right, so let's look at each event B such that B doesn't equal A. If A and B are in a collision, what does that mean? So if event B and A don't collide, meaning that they don't share some time, then our solution equals 0. So then our solution equals the max of whatever our previous solution is, or the value of A plus the value of B. So all I'm basically saying here is like, I look at each event A, I look at each event B that isn't A, I look at both of those events together, and I say, okay, if they don't share time together, then that means that these could be two events that I choose, right? So this is going to be n here, right? Because I have to look at n events here, and then for each n event, I have to look at n other events, n minus 1, because of the event they're not. So this is where we get this n squared solution. Okay, so the way to kind of fix this problem to make it faster is, well, we definitely have to look at each event at least once, right? So intuitively, we know that we're going to have something with n. Now, can we shorten this process here? Can this process be shortened? Okay. Well, if I have an event A, okay, and it has a start, and let's just think about it in terms of what it actually is. So there's a start time for A. I don't like that color at all. I can't see, apparently. Right, so there's a, ooh, that looks good. There's a start time for A, there's an end time for A, and there's a value associated with A. Okay. Now, in order for A to meet with somebody else, right, we have to look at the events that come before A and after A. But in terms of how A works, right, this event, this event, right, this event has to either, any event that I compare A to, right, so any event B is either on the left side of A and its end time of B, the end time of B has to be less than the start time of A. Let's do that again. So the end time of B, let's make this green, I guess. So B, end time of B, value of B, right? In order for something to be a candidate of A, if its start time is before A, right? So it's to the left of A, this event starts before, this event B starts before my event A starts. In order for it to be something I can compare to A, its end time has to be before start time of A. Does that make sense, right? Because it definitely starts before me. So the only way that it doesn't collide with me is if it ends before me. Okay? Now on the other side, on the flippity dippity dip, I could also have an event C, and if, sorry, I heard my phone, I don't know where it is. If I have an event C and it start time of C, end time of C, and value of C. I can also consider this event, since I'm putting it to the right, I'm trying to disclose that it starts after me. Right, if it starts after I start, right? So if these things are sorted in terms of when they start, right? So if this thing starts after I start, then it better start after I end, right? Because I have start time of A. So we put it in this little system here because I'm guessing what I'm saying doesn't really make a lot of sense. Okay. So the end time of A has to be less than the start time of C. And I hope that makes sense, right? This is definitely true, right? Because when my system ends here, when A ends, it has to end before C starts. That's the only way they won't collide, right? Because we're already assuming by the way that we've drawn this that B starts before A starts before C, right? That's why I wrote B, A, C. So if my system ends before his system starts, then it's a possible candidate, right? So that's kind of just this idea of the events not colliding. So maybe that doesn't add a lot of value. Well, if we instead said, let's look at this left side here. And we said, well, the value of B, right, is the value that I'd get if I chose B. But what if the value of B was instead the maximum score I could get up to B? Meaning, imagine that there was a prefix sum where when we had events like B, A, C, and imagine B had value 1 and this had value 3 and this had value 2, right? Because what I want, if I'm choosing A, right? Let's say I'm choosing, let's add some more. If I'm choosing A and Z has value 4, right? I'm going to choose, if I'm considering people that start before me, which are Z and B in this example, right? I have to pick from one of these. Now, as long as they end before I start, if B ends before I start and Z ends before I start, I should choose Z, right? But if these are ordered such that Z ends before B ends, that means if I can choose B, I can also choose Z. So I might as well choose Z, right? I just want something that's in this system, right? I want what I really want is the max value I can get from something that ends before me. That ends before I, meaning A in this example, start. So if I just keep track when I go left of the maximum thing that's seen so far, when I look at A and I get value 3, I can add in 4 because 4 is the maximum thing that happens before me. So this is kind of like a prefix sum idea, right? So if I have this system A, and imagine that there's other nodes here, B prime, B double prime, B triple prime, I don't know, right? What I want is just like, if I'm taking this event here, A, all I need is the maximum amount of points I can get from anybody to my left, right? If anybody ends before I start, right? If this person ends before I start, so I don't even need to assume that start B is before start A. I just thought about that right now, right? Because if it ends before I start, it definitely starts before I start. So if this ends before I start, I just need to find the maximum value I can get from any event that ends before I start. So if I do a prefix sum and I find the maximum element that's less than me, so I find that the element that I find the event that ends right before my event starts. Right, so if I have a system, let's do one more example. And let's say that these things are sorted in terms of end time. Okay? And I look at the value C. And let's say that C's like this. The start time is 4. And let's say that all these things I'm talking about, end times equals 3, end time equals 6, end time equals 7, end time equals 11, end time equals 12, end time equals 15, end time equals 2, end time equals 5, or 1. So, okay. So I have C start time equals 4. If I'm looking just to my left, right, I'm saying, okay, who can provide me with the, who to my left, whose end time can provide me with the maximum number of points, right? So I look at C, and C gives me, so let's say C has value 7. This has value 1, 3, 2, 4, 5, 5, 6, 1. I don't know. I'm just making up numbers. For C, what's to the left of C? Well, C starts at 4. So the maximum event that ends before my event starts, so the closest event to my event is B, because it ends at time 3. Right? So that means that everybody who's to the left of B in terms of end time could also be chosen, right? Because B ends at 3. I start at 4. And the way that I have this system set up, it's in order. So everybody to the left of B in this setup also has an end time that's less than my start time of 4. So they could also be chosen if I choose this event C equals 7. So ideally, I should choose A because A has value 3. So if I just keep track of the maximum score you can get from the left, then when I just choose B, I can just choose this value 3. So that's as best as I can explain the solution. So then how does this become efficient? Well, since this system is sorted, right? Since the end time is given sorted, when I look at an event like C with start time equals 4, I can just use binary search to find the maximum event where its start time is less than 4. So I do binary search, and I look for an end time that's less than the start time of C. So I start in the middle, and I say, okay, end time equals 7. Okay, that's obviously too big. So then I go here, and I say end time equals 3. And then I go here and do binary search on this system. Okay. So the way that we're going to do this is there's an idea of a prefix sum to get, you know, the biggest end times you've seen so far. So you can always select the largest one. Now, before I actually go back to that, one last point. You know, we had this idea of looking at things to your left, right? And looking at things to your right. But since we're only choosing 2 events, we can always just look at events to our left. Because you choose a node, you look at one to its left. That's identical to choosing a node and looking at one to its right. Right? Like, if I had A, B, and C, X, A, B, C, and Z, imagine that the 2 optimal were A and C. Right? When I run this problem from A, if I looked at the left and the right, it would choose A and it would choose C as the optimal. But then if I looked at this problem from the perspective of C, and I looked at the left and looked at the right, it would choose C and it would choose A. Right? So it's just doing the same thing twice. So you only need to look in one direction. Right? So you can just always look to the left of an element. So when you choose A, it would try to choose X, I guess, depending on how the system works. And then when you look at C, it would choose A, and then you would get the true optimal. So you don't need to look in both directions. You only need to look in one direction to make this work. Okay? So we have to use a prefix sum to get the best value up until a what do they call it, last time or something? End time. We need to sort our times, our events, in terms of end time. That way we have a system, right, that looks like this. This is gonna try to open, and then who knows what's gonna. Come on. Okay. Why are we doing that? Right, because we want to have our end times looking like this system here. That way we can traverse based on end time and make a statement about, well, remember we said that we were looking for end time less than 4. The best event with end time less than 4, the closest thing is B, which is 3, and that'll have information saved about the best value I can get there. In terms of end time, run binary search to find event with end time closest to start time of chosen event, right? So you always look at each event, you look like you chose it, and then you look at all the events that come before it. And then choose each event and look at best with start time ST, and choose best event with end time less than start time using above approach. So what's the runtime of this now? Well, to run binary search, right? So now when we run this system, how did this even get over here? Right, so before this was O of n, because we'd have to look at each event. But now we just run binary search to find the event B that's as close as possible to A with terms of its runtime, and that takes O of log n time. So now the whole runtime of the system is O of log n. But we also have to do some sorting at the top, which is also O of n log n. So this is O of n log n solution. Okay, so let's first sort our events in terms of end time. All right. So to do that, we'll just take events and we'll sort it. And then the key will be, we'll take the event, and then we're sorting it based on end time. And to do that, we just take, that's the 0th value, the first value of this system, right? Because this is index 0, index 1. So now the end times are sorted in terms of the event. To run prefix sum, how are we going to do that? We could just say, there's a lot of ways we could do this. A lot of dumb ways we could do this. So let's just call this best end time value. It's going to be the event's value, right? Because that's the value you get from the event for each event in events. So we'll just make this a little bit cleaner. So this is start time, end time, and then value. And then we'll run prefix sum, like a prefix sum, right? In range 1 to length this. So this at I equals the max of itself. Put me over here. The max of whatever it is, and the previous value's best end time. All right, now we need to run binary search to make this work. So I'm just going to run through a quick binary search. So we'll call it BS because this problem is BS. So we have a lower index, a higher index, and a value that we're looking for. And we want to get the closest thing that's up to this value. So we'll set our medium equals to low plus high divided by 2. That's normal. If the low equals the medium, and you can run through binary search to see if this makes sense for you. If the low equals medium, that means that you've kind of exhausted and you've gotten as close as possible till you can get to the value that you're looking for, right? Because low would keep moving up, and you have low equals medium. That would mean that low and high were one apart from one another, right? That's the only way that would happen, because you'd have to have a difference of 1 in order for low to be equal to medium. So then you got as close as possible as you can get to the starting time that you want. So this is then the event with the closest end time. So if that's the case, then you return best end time value at this node. Otherwise, if what? We want the end time of this system. So the events at medium, we want its end time. So that's a 1, right? So that's the end time of this event. If it's greater than or equal to because we want the largest one that's less than us, right? So if it's greater than us, we need to move down, right? We need to get smaller. If it's greater than us or equal to us, we need to move down and get smaller, right? Because we don't want it to be equal to the start time. It has to be 1 less than the start time. At most 1 less than the start time. Is greater than or equal to value. We'll call this start time, just so it's a little clearer. Then we're going to return BS on, well, we'll have the same low value, but now the medium is the high value, right? So you're just moving like very basic. Otherwise, if what does this mean? The start time is too small. Dude, I get so confused when I do binary search. I don't know why. All the topics I've grown to familiarize myself with for whatever reason. Okay, so I want to find maximum end time, which is less than the start time that's given. Okay, so if I have end times like 6, 8, 10, and 11, and I'm looking at start time equals 9, the answer would be 8. So if I'm looking at medium is 10, my start time is, let's say this was 9, just for the sake of making this really complicated for myself. If start time was 9 and this was 9, then I need to go to the left. So if start time is less than or equal to this end time, okay? So if start time is less than or equal to this end time, I need to go to the left. What if start time was 12? Well, I need to consider the fact that it could be bigger, so I need to go to the right. Okay. Sorry. This is very common for me to make. Like, I've done like, you know what I mean. It's just crazy that I still have so much trouble with binary search. Okay. So that's the run binary search, and then we'll just have our solution s equals 0. And then we'll look at each node. So the start time of the node, the end time of the node, and the value of the node in events. So we'll look at each event. And then we'll say what? The solution is the maximum of the solution that we found so far. The value of using this event plus the maximum event I can get, low equals 0, high equals length of events. And the start time is my start time, right? So the maximum event that ends before my event starts. So that's this here. This problem is so... I can't believe this is a medium. For me, this is a hard, and this is like a hard. But I think it's because I'm just not very good at binary search or seeing when it needs to be used. Okay, so I sort the events. I look at each value and I say, okay, the best value here is whatever you are, and whatever the previous thing's best value was. So if low equals medium, then I figure out what's the best up to this point. Low, medium, medium, high. Okay, the problem is that you could have a single event. No. Oh. I think I need to add a an additional event that ends at time -1 and gives you 0 points. That way there can be single events that have maximum time, but that doesn't. This doesn't address the fact that I see. Try to package them incorrectly. I don't even know what's going on. Which is always great. Alright, so let's just run through a bunch of debugging. Sorry, I look like a fool. So let's see if the best end time values are right. There's only 3 events, yet this says there's 4 events. Oh, because it's adding an additional 0, because it already has a 0. Because I've already created the events. Alright. So I think this is right. Let's go ahead and pray for the best. Where's the prayer? Oh, right. There you go, 69. All right, so why did I add this additional 0 event? Well, you need to have a place for your system to go. So this is just the fact of binary search, right? If your events are like this, where like this is a real event and you know, there's no event that can match with B. There's no event that can match with B. The way that our binary search is set up is it'll just force match with A even though their times don't match up. So you put a buffer in here with value 0. That way when B matches up, it gets forced match with this if nothing matches with it. So it's just the fact of this binary search the way that it's working. But yeah. So runtime of this, we've already established is n log n, right? Because you have to look at each n event, and then you have to run a log n operations to find the event that would correspond to it. In terms of space, we don't add any space here. We add 1 element here, and maybe this adds n, but you know, you could do this with just adding 1 element. But here you have to add n elements for the prefix sum. So n space, n log n, runtime, right? The sort is n log n as well. Okay. All right, guys. Sorry about today's video. This was a really difficult problem for me.